All traffic barrier safety systems need end treatments. Roadside barriers, median barriers, and bridge rails, flexible, semi-flexible, or rigid barriers, any type of barrier must have end treatments. The video you're about to see will examine 4 different end treatments. First, the breakaway cable terminal. Second, the flared and buried. Third, the twisted and turned down. And finally, the Sentre end treatment. In another session, we saw how barrier systems are designed to slow, stop, or redirect vehicles. The entire barrier system must act as a single unit for it to work correctly. Each part of the system, the standard section, the transition section, and the end treatment is important in assuring that the function of a barrier system will be carried out. But end treatments are probably more important than the other 2 parts. Why? The end treatments anchor the upstream end of the system, and when necessary, the downstream end as well. If the end treatments fail to function correctly, the entire barrier system could fail. If the system fails, motorists could be killed or seriously injured. Because the end treatments are so essential, special attention must be given to their proper installation, maintenance, and repair in traffic barrier systems throughout the United States. To help us understand end treatments better, the videotape opens with a look at how the type of barrier system is chosen for a particular location, and then looks at each of the 4 end treatments.
Traffic barrier safety systems, whether they be roadside barriers, median barriers, or bridge rails, all need an end treatment. It makes no difference what type of barrier is involved. It can be flexible, semi-flexible, or rigid. All must have some form of end treatment. In this program, we'll look in some depth at 4 end treatments: the breakaway cable terminal, the flared and buried, the twisted and turned down, and the Sentre end treatments. Barrier systems are built to slow, stop, or redirect cars that hit them. This requires the design and construction of a barrier system that acts as a single unit when called on to do so. All parts of the system, the end treatment, standard section, and transition section, are important in supplying this required action. However, end treatments are probably more important than the other 2 parts. Why? Mainly because they anchor the upstream end of the system and, when designed to do so, the downstream end too. But also because if they fail to carry out their function, then the entire barrier system could fail. And if the system fails, passengers in the car involved in the impact would probably be either seriously injured or killed. So as you can see, particular emphasis must be placed on the proper installation, maintenance, and repair of these vital parts of the traffic barrier systems in use throughout the United States today. Before we review the 4 end treatments that are the subject of this program, let us quickly examine the factors that influence the selection of almost all traffic barrier systems. When designers survey a location where it's felt a traffic barrier should be installed, they make their recommendations for the type of system to be used based on 6 major considerations. These are the type of hazard the motorist needs to be shielded from, the available distance between the barrier and the hazard, how the barrier will have to be located in relation to the traffic it'll be designed to protect, the maintenance that will be required to ensure the system is kept working correctly, the estimated cost of installing and maintaining the system, and finally, the type of systems in use in the highway agency in question. Now to the systems. The breakaway cable terminal end treatment is designed to work with W-beam barrier systems, but can be transitioned to work with the tri-beam through the use of a commercially available transition piece. The roadside barrier breakaway cable terminal, or BCT, is designed to break away at the first 2 posts and allow the vehicle to accordion the W-beam and pass safely behind it. To allow for this momentum slowing action requires a finely tuned BCT system, the first post of which will shear off at a pre-planned point where a hole has been drilled in the wood post system. or where a slip plate has been installed if the system is supported on steel posts. After being hit downstream from the terminal, rail strength of the system is maintained by tension in the cable. There are 7 key elements that will normally determine whether or not the BCT will function as designed when impacted. These elements are post dimensions and the actual spacing of the posts, cable size, attachment, and tensioning. The breakaway system, either the hole in the wood post or the slip base on the steel post, footings of the first 2 posts of the system, the 4-foot parabolic flare in the last 37.5 feet of the rail, a critical element, the hardware used to connect the system, and available recovery space behind the end treatment itself. Post size and spacing are obviously very important. If posts are too small, they won't provide the designed-in resistance when hit. If they're too large, they'll resist too much. Approved wood post size for the BCT is 6 by 8 inches. Normally, a Douglas fir post is used. Steel post measurements are 6 by 8 1/2 inches. Posts are set on 6-foot 3-inch centers. The first 2 are not blocked out to prevent fouling on impact. Although no more than the first 37.5 feet of rail functions as part of the system, the flare must be maintained beyond this point if so designed. The first post of both the wood and steel post BCT systems should be drilled with a 2 3/8 inch hole. On wood post systems, the cable, attached by 8 bolts to the back of the W-beam section ahead of the second post, passes through the first post and attaches with a plate to the front of that first post. A steel insert is used through the drilled hole to keep the cable from tearing the wood post. The cable must be kept tight. 3/4 of an inch of deflection is acceptable. For steel posts, the cable passes through the first post above the slip base. The plate extends down to the bottom of the lower stub plate so that the slip base is not activated by cable tensioning when it's impacted downstream from the end. When the system is impacted on the end, the wood post breaks away. In the steel post system, it slips away. And this action releases the tension in the cable, allowing the W-beam to buckle. Depending on the size, weight, and speed of the impacting car, beams in the end treatment continue to buckle until the vehicle is stopped. A bulb on the front of the system is intended to distribute a head-on collision's weight and force. It flattens out, preventing the W-beam rail from spearing the impacting vehicle. Here's a new bulb just prior to installation, and one that's been hit and done its job. To make sure this bulb functions properly, care must be taken to see that the wraparound connection on the back of the W-beam is tight and that all bolts have the right-sized washers. Otherwise, the bulb could tear loose on impact and the W-beam could spear the vehicle. To ensure that the first and second posts of the system break away and are not pushed over when impacted, they're set in concrete footings of at least 3-foot depth. The surrounding soil must be stable. A loose sand will not work. Removal of broken stubs has created some problems, with several solutions being worked out. A styrofoam sleeve and a steel sleeve with soil plates are 2 different concepts available. Another solution has been to place a heavy pressed paper tube around the post when it's installed. The footing is poured around the outside of the tube. Now, care must be taken to ensure that no concrete is placed between the tube and the post. Once installed, the paper tube absorbs water from precipitation and is softened so that the post stub pulls out easily. Much of the tube comes out with the stub. The remainder can easily be removed from the hole since it does not adhere to the concrete footing. Stub posts can quickly and easily be removed from this type of footing, which meets installation specifications. Flare characteristics of the BCT are critical to its proper performance, particularly with the smaller vehicles that might impact the system. Head-on hits with unflared roadside barriers can cause severe damage to these smaller cars. Flare for the BCT must be parabolic with a 4-foot offset from the tangent section of the railing. Length of the BCT is also a critical factor in its reducing injuries and deaths when hit. Recommended length is 37.5 feet. Some agencies have extended the terminal length to 50 feet, anticipating the extra length will offer more energy absorption capacity. However, since the BCT is intended to divert an impacting vehicle to one side of the barrier rather than absorbing its kinetic energy, the extra length provides no added capability. Connection hardware for the BCT system simply cannot be changed from what is required by specifications. If even minor changes in bolt size or strength are made, the system will normally fail to function as designed. 8 bolts must be used to connect the cable block to the rail. Cable anchorage at the first post must be accompanied by a 3/8-inch plate. Beam splices must be lapped in the downstream direction to avoid snagging an impacting car. All bolts must be the proper size and must be tight. After the first 2 posts, blockouts should be used. No washers should be used on the first 8 posts of the W-beam post connection bolts. This allows the railing to tear loose from the post and to bend outward more easily on frontal impact. Leaving off the washers on all post bolts is acceptable practice. Check your specifications for guidance in this matter. Finally, recovery space is a major consideration when a BCT end treatment is used. Obstructions like the utility pole shown here cannot be located within the treatment. The whole idea of the BCT is that it bend backward when impacted near or at the nose. Common sense then dictates that there be an area behind the treatment that will allow the impacting vehicle to regain some degree of control. This is not possible if there's no recovery room available behind the system. The driver would simply be trading the frying pan for the fire. So the area behind the BCT should be free from any fixed hazards and as flat as possible so that no secondary impacts will occur. No signs or other roadside obstacles should be placed within 200 feet of the BCT. Terrain leading to the barrier needs to be as flat as possible so that any impacting vehicle hits it at the proper height. The flared and buried end treatment is often used when the fear of spearing is a concern. How does it accomplish this task? The end of the treatment is simply buried and anchored in a cut section. However, there are still some considerations that must be dealt with in this end treatment procedure. First, the flare must be correct. And in using the design, particular care must be given to maintaining proper barrier height. This might present some difficulties, particularly if the treatment must cross ditch lines. Also, if a cut slope is being used for burying the end, long sections of railing may be required if the cut slope is located some distance from the roadway. The barrier height problem simply means that if the top of the rail is too low, the impacting vehicle may vault it. And if it's too high, the vehicle may go under the barrier. Both of these possibilities must be avoided. Anchoring of the system is normally accomplished by the upstream end being bolted to a concrete footing in the cut. 8 bolts are normally used, providing positive connection to develop the full tensile strength of the rail. Then the slope is restored to its normal shape. Various designs of the twisted, turned down Texas twist and anchored end treatment have been used in several states. For our purposes, we'll call this end treatment the twisted and turned down treatment. The major problem with developing this system has been with cars vaulting and or rolling over. This occurs if the impacting vehicle rides up on the twisted section of the system and crosses the first backup post. Modifications to the system have now made it a workable one. Basically, what has been done to correct the problem involves removal of a post and rigging the railing so that it can fall down when impacted. This is called CRT, or Controlled Release Terminal. One variation is the clip and short section of W-beam. Other variations perform in the same manner. Fundamental to the system's working as designed is the requirement that the rail release from the supporting posts as soon as the end treatment is loaded with a downward force. Various rail post connections are used. To set up the system, a short section of W-beam is bolted to the posts. The barrier railing is then placed into this section and rigged to be held there by a weak galvanized steel clip over the top rib of the rail. Any significant downward load on the railing, such as the weight of a car, pushes the rail down from this connector and allows the W-beam to fall harmlessly to the ground. The impacting vehicle then either continues on to shear off weakened posts or until it decelerates to a stop in a runout area behind the rail end treatment. With this system, spacing of the first 3 posts is important. The twist and turn down occurs in the end 25-foot section. No post should be set within the twisted section. The second and third posts are spaced 12.5 feet apart, with remaining posts set at 6-foot 3-inch intervals. After passing down the first section of rail, the 25-foot section, the vehicle will either shear off or knock over the first 3 posts, depending on whether they're wood or steel, and slowly decelerate to a stop. The twisted and turned down end treatment should be flared out at least 2 feet, preferably 4 feet, to be operationally functional. The turned down end of the system should be anchored by 4 bolts to a concrete footing that's either at or below grade level. As mentioned earlier, the rail is intended to release from the first post and lie down. To bring the required quick release, several systems have been developed that work like these galvanized steel clips. A recent addition to the guardrail end treatment is the commercially available Sentre guardrail end treatment. This system combines features of other end treatments along with those of some crash cushion units. It has support posts with slip bases, collapsible thri-beam fender panels, containers of sand on the first 3 posts, a cable terminal that assists in the slowing of the impacting vehicle while at the same time redirecting it, and a soft nose that collapses on impact, doing away with spearing dangers. When impacted in a head-on crash, the system's fender panels telescope in, the support posts shear, and the cable of the system activates to redirect the car into its normal travel lane or slows and stops it. The sand containers on the first 3 posts of the system assist in the deceleration of the vehicle. Installation of the Sentre is relatively simple, as the manufacturer's installation instructions are complete and well illustrated. When combined with a standard work order and work plan, sufficient information on system installation is available to make putting the system into service an easy task. The tools and equipment required for Sentre installation are listed in the instruction manual. In anticipation of this installation, a level platform must be poured with a square anchor installed in the front and a rear anchor off to the side with its own concrete base as specified. The Sentre unit may be installed either on straight guardrail or on guardrail that's been flared away from traffic. 2 types of slip bases are supplied for the unit. The slip bases for posts 1 and 2 have flared slots, while the slip bases for posts 3, 4, and 5 have straight slots. Arrange the bases next to the proper post locations with ramp ends touching the ground before proceeding to the anchoring process. 4 basic anchoring alternatives are suggested by the manufacturer for the system. The first option involves driving a wooden post with a platform attached to the top of the post. The second option uses steel I-beam driven into the ground to anchor the unit. The third option calls for embedding L-bolts attached to the slip bases in 4,000 psi concrete footings. The final alternative uses expansion-type or flush-type anchor bolts to fasten the Sentre to a 4,000 psi minimum concrete pad. The manufacturer supplies additional anchoring information with the system. It should be reviewed along with your own state standards for anchoring procedures recommended for your area of the country. For purposes of demonstration, the concrete pad method will be shown in this program and how this particular crew performs their installation. Assemble post 1 in place first. Mount the base to the concrete by drilling the hole and then tightening down the bolts. Next, place 4 hex head bolts head down in the base slots with a flat washer on each bolt. Then place the keeper plate onto each slip base, followed by 1 flat washer on each base plate bolt. Position the post base over the bolts, followed by a flat washer and nut. Torque the nuts to 75 foot-pounds plus or minus 5 foot-pounds. Careful alignment of the slip bases is extremely important. They must be aligned to each other as well as to the finished grade of the road. Check alignment parallel to the roadway once all 5 bases are in place. Posts 1 and 2 are similar except for the cable hole in post 1. Posts 3, 4, and 5 are different from posts 1 and 2 and must be positioned accordingly. Next, attach a blockout with the 2 hex head bolts and nuts called for and tighten firmly. Once all posts and bases are mounted, then it's time for the mounting of the fender panels. Bolt a fender panel to post 5 using 2 hex head bolts, a flat washer, and a nut. Be sure to use the holes marked with the letter S. This fender panel will overlap the transition panel or tri-beam guardrail end. A 3/4 inch diameter hole should have been drilled in the transition panel end or the tri-beam guardrail end. If not already done, this hole should be drilled approximately 1 inch from the end of the slot in the fender panel. Place the mushroom bolt assembly through the fender panel and transition panel and secure it with a square washer and nut. Then tighten the mushroom washer nut to 60 foot-pounds. Remember, use holes marked S. Attach the remaining panels, starting with post 4. First, attach the panel to the post with 2 bolts. Then attach this panel to the previous panel using the mushroom bolt assembly. Continue the process for the remaining posts and panels. At post 1, the 3/4 inch bolt assemblies must be left loose. The plastic bull nose is positioned over the panel but under the flat washer and bolt head before tightening the bolt assemblies. 2 bolts are also placed through the 2 remaining holes in the bull nose and through the 2 fender panel holes labeled G. The cable is now ready to be connected. Place the front threaded end through the first post and on through the anchor. Install 1 square washer and nut on it. The rear anchor threaded end must go through the rear anchor, using as many square washers as necessary to install the nut without bottoming out on the threaded section. Tighten the cable by holding the swagged end with a pipe wrench and torque the nut with a torque wrench to 100 foot-pounds. The nut threads need to be fully engaged to the threaded cable ends. Next comes sandbox placement. The sand containers are attached to posts 1, 2, and 3 and are labeled with their proper post numbers. Place the correct container on each side of these first 3 posts. Use 2 bolts, 4 washers, and 2 nuts to attach the containers, sandwiching the post and blockout between the containers. Fill the containers with clean, dry sand to the top edges and snap the lids closed. After completing the installation of the redirecting cable, check to ensure that all fasteners are fully tightened throughout the unit, on the fender panels and other system parts. For future maintenance and repair of the system, the manufacturer of the Sentre unit provides well-designed procedures. At times, there simply will not be an appropriate end treatment available to meet a traffic safety need. That's when a combination of both a barrier system and a crash cushion system might do the trick. Crushable crash cushions can be used with some special needs, but the most common use of combining crash cushions with end treatments will be when they're used with rigid systems, such as the concrete traffic barrier. A final word, this concerning the installation, maintenance, and repair of these systems. Don't ever feel that you must memorize how all of these systems must be serviced. That's absolutely not required. What you do need to know is where to find the specifications that will apply to the system you're working on, along with a basic knowledge of how the various systems work. A checklist is particularly helpful in doing your job in a systematic manner. If you follow both your local standards and any available manufacturer specifications for the installation, maintenance, and repair of these end treatments, you'll be able to walk away from the job knowing that you've done your absolute best to protect the motoring public.
As you've seen, the proper functioning of end treatments contributes to the functioning of the entire barrier system. Another component of the barrier system that we haven't covered yet is the transition of roadside and median barriers to a bridge rail. So we'll understand the role of transitions, we'll look closely at connections with bridge rails, stiffened transition sections, and other transitions. And our exploration of transitions will help you be able to know why transitions are necessary, learn how transitions function, and point out the key elements of good transitions. The change from a standard section of barrier to a bridge rail requires a transition section to account for the differences in dynamic deflections. In other words, the transition is used to change from a barrier of one stiffness to one of another stiffness. In doing this, transitions accomplish three goals. First, the transition provides continuity in strength between the different barriers. Second, it provides a smooth connection that allows redirection of vehicles without their snagging on or penetrating the barrier. And finally, the transition helps maintain vehicle stability to prevent vaulting or rollover. Here, you can see a totally unacceptable transition. Its upgrading should have a high priority. The end anchorage at this concrete bridge rail was not strong enough to provide continuity of beam strength from the W-beam to the bridge rail. As a result, the W-beam tore loose at the connection, and good connections to the bridge rail are always necessary. To get a stronger connection, drilling completely through the concrete section and using a steel backup plate or heavy washers would provide good anchorage. Here you can see a transition connected correctly. The W-beam and end cap connections are correctly installed. All the bolts are in place, and the W-beam is correctly lapped for the approach rail. The concrete parapet wall must be strong enough to transmit the beam loads. The concrete may break if it is not reinforced. And here you see a situation where the concrete did break. The bridge rail must also be structurally sound. In order to be sure of a strong connection, it is wise to go farther down the bridge for a structurally adequate anchor. This box beam transition to a concrete barrier appears to be smooth, but the deflection characteristics of the two are drastically different. The box beam, on weak posts, has been anchored on the second concrete half shape. The first section of the half shape has been flared behind the box beam. Here we see a vivid illustration of the danger of an erratic transition. When the place of transition was hit by a truck, the box beam smashed into the first section of concrete. Because the concrete sections weren't connected, the first section was easily knocked over, and then all continuity along the barrier was lost. These half shapes turn over easily, so the sections must be tied together for more stability. In the previous photo, this transition appeared to have all the right features, but it failed to perform because of the inadequate end connection between the sections of concrete barrier. Stiffening the transition between barriers of different deflection characteristics could be accomplished in several different ways. Here is an example of reduced post spacing, the most popular method of stiffening metal rails. You can see that the last 25 feet of barrier is supported on blocked out posts on 3-foot, 1.5-inch spacing, or half the normal 6-foot, 3-inch post spacing. In addition, the last 4 posts have 19-inch spacing, so the W-beam becomes progressively stiffer as it approaches the rigid concrete bridge rail. The Federal Highway Administration has developed an improved transition design to address the need for a high level of transition performance. The design includes W-beam barrier, C-section rub rail, barrier end anchorage, bridge rail functionally and structurally adequate, blocked out connection, and reduced post spacing. Stiffening features aren't the only concerns for transition performance. The alignment of a transition is also important. Transitions with reverse flares may pocket a vehicle. Here, the bridge rail end section was flared away from the roadway and transitioned from conventional safety shape to a vertical face at the upstream end. The W-beam is installed flush with the safety shape face, and the end of the concrete parapet wall is tucked back under the W-beam to prevent wheel snagging. It's too bad that the end cap is incorrectly lapped. Unique transitions such as this box beam to a bridge rail can be accomplished with specially manufactured transitions. This installation has all the best features of a proper end anchorage. The blocked out anchor protects the corner and provides a smooth transition. Strength is provided, and the tapered end section of the concrete barrier from normal shape to vertical face eliminates wheel snagging by positioning the concrete barrier end well back under the blocked out W-beam barrier. To see how well transitions work and the reasons why they fail, we'll watch this film on bridge railing and transition crash tests.
These series of tests were run to determine the safety of bridge railings and W-beam transitions into bridge rails. The test specifications were a full-size sedan traveling at 60 miles per hour, hitting the railing at a 25-degree angle. This is a standard concrete beam and post railing. Note the open joint. It allows the vehicle to snag on an undeflected post and beam end. This railing definitely was not a success at redirecting the test vehicle, failing the functional adequacy criteria. This is a 42-inch, 3-rail galvanized steel railing. One of the open sections of the rail is at hood height, which causes the test vehicle's hood to snag on the post and be driven into the windshield. Here is a deck-mounted 32-inch 2-rail aluminum railing. There are problems with the arch in the post's base plate and the riveted post-to-base plate connection. This is a retrofit of the previous railing. The base plate has been flattened. The test car is successfully redirected. However, this railing is still below specification strength requirements. This aluminum railing is mounted on a brush curb and has 2 rails. The height of the railing is 38 5/8 inches, including the brush curb. The test vehicle hits at a 15-degree angle. There is tire scrubbing on top of the brush curb and tire snagging on the posts, causing a rollover. This lower rail was 4.5 inches too high, which surely contributed to the snagging. This is a tubular thri-beam railing, 33 inches high, mounted on rigid steel posts. It is a success at redirecting the test car. This standard bridge rail consists of a W-beam guardrail section backed up by 2 box beams mounted on steel breakaway posts. The tensile continuity of the rail makes the system work. This railing also redirected an intercity bus going at 60 miles per hour, hitting the railing at a 15-degree angle. This is the experimental SERB, or self-restoring barrier. The self-restoring features are the tilting lever support arms that allow the barrier face to move up and return to its original position. This version has a 34-inch mounting height. The test vehicle is successfully redirected. This is a standard safety-shaped concrete barrier with an aluminum rail on top. The aluminum railing adds another 12 inches. Notice the shape of the barrier face, which sends the hood over the top of the railing and prevents snagging. This test is with the same kind of barrier. The test vehicle leaves the ground but is successfully redirected. This is a test of a typical transition from a guardrail to a bridge parapet. There is no offset between the concrete wall and the W-beam rail. The results of this test are disastrous. This is a retrofit of the previous design. 2 more posts have been added, so the first 4 posts are closer together. A W-beam rub rail has also been added. The test vehicle is successfully redirected. However, you see the W-beam was damaged at the end of the parapet. As a result of these crash tests, the Federal Highway Administration has recommended that all bridge rails be tested under full-scale crash conditions before being placed in service. Additional testing of transitions is underway.
We need to reduce the severity of accidents at transitions. One technique for reducing vehicle snagging at the rigid concrete bridge rail end can be seen in this next photo. A short section of W-beam is placed under the standard section to act as a rub rail. You can see that the rub rail is also anchored securely to the bridge rail face. The upstream end is tucked back under the approach rail beyond a post. Vehicle stability at transitions is affected by many factors. Some of them to watch for are listed here. Vehicles can ramp on curbs and sidewalks that project out beyond the anchorage point, as in this photo. The marks on the curb face and on the wing wall at this bridge indicate a history of repeated hits. The approach rail should be blocked out flush with the outwardmost projecting part of the bridge rail. In this case, the approach rail should be flush with the front face of the raised walkway. Blocking the approach rail out to the front of the concrete safety walk protects against impact with the corner of the walk. This approach rail is well anchored to the bridge rail section for good beam strength continuity. Unfortunately, the rail is lapped incorrectly. Transitions need to be checked in both directions. Sometimes improving the transition in one direction results in a potential hazard in the other direction. We're going to look at a before and after situation. Here is the before. The transition from a standard section to the bridge rail ends at the offset block a short distance across the bridge. In this after picture, you can see the smooth transition after the barrier is extended across the bridge. When barriers need to be stiffened, they should be stiffened in a way similar to the transitions. Barriers can be stiffened by decreasing the post spacing. Backup sections can also stiffen the rail if this doesn't create a new hazard. The end of a backup plate should be at a post or lap where cutting wouldn't happen. These are some of the key items to consider when building transition sections. Each should be evaluated before installation and then again before the roadway is open to traffic. One of the most common adverse effects on transition performance is inadequate end anchorage of the approach barrier to the pier or bridge rail, as you see here. This area should have full beam strength. What corrections should be made at this installation? The end should be tied in the bridge rail. Posts should be added at the transition. A rub rail should be installed. A straight flare should be added to provide deflection in front of the light pole. The rail should be blocked out to the face of the safety walk. This repair should be done as soon as possible. Until it is, it should be marked with barricades. Now this is an excellent installation. You can see the smooth flare rate, the decreased post spacing throughout the transition section, and the anchor point blocked out to the curb face. Although it's not absolutely necessary, an end shoe would have improved the aesthetics. After the installation, maintenance becomes essential to guarantee performance. Maintenance staff should be aware of these special considerations needed to maintain transition sections. Good maintenance goes beyond simple repair. We need to look for opportunities to improve installations, and then talk to designers and construction staff about these ideas. One maintenance issue to pay attention to is post support, because adequate post support is absolutely critical. You see here a situation where the design did not fit, so half the flange and web were cut away to fit the post around the curb. At the transition to the rigid bridge rail, where post strength is needed most, there is now very little. And here you see many errors in installation. A weak bar connection, a connecting bar that is too small, no connection to the bridge rail, and a weak bridge rail. This approach rail needs to be extended to the next concrete block, and the end of the approach rail needs to be secured to the next block. Blockouts should be used to line up the approach rail with the curb. In this well-installed transition, the transition stiffening and blockouts are obvious. And this is a poor structural connection because, as you can see, the installation doesn't have all the bolts called for on the end shoe. Here is an obvious field fix. This is an untested transition with visible potential for snagging. And here is a good use of a rub rail in a transition. In this last picture, you can see obvious pocketing problems in this poor transition. Throughout this session, we've talked about the importance of correct installation and maintenance of end treatments and transitions. As you've seen, the smooth functioning of these safety features as designed depends on understanding what the design is intended to do. As you saw in several of the last pictures, common sense field fixes are not usually a solution to installation and maintenance problems. Each safety feature has its own unique requirements, and in the next session, we'll learn the functional requirements of other safety features.